Hi, how are you? How's everything? Okay, this is our fifth experiment, and according to our syllabus, the fifth experiment is Newton's second law, the Atwood machine. Then, once again, we will be using a simulation to conduct the experiment. Of course, we will still be using our manual, but of course, we are going to make a little bit tweak here and there, because the simulation might not be really a direct interpretation of what happens in our physical lab. Okay, so having said that, the experiment is going to be, the perfect replica of what can be done in the lab, except that there will be a few changes, like when it comes to the numbers and things like that. Okay, so once again, please follow me and follow this procedure and try to complete the data table. And once again, you write your report, and then you will go ahead and then submit your lab report online. Okay, so the first thing is I would like to give you some kind of like background, what we're going to do with this experiment. So basically, what Newton's second law states that, we already covered that in the theory. What it says is like, net force, which is a vector equation, is equivalent to mass times acceleration. All right, so the net force acting on an object is directly proportional to the amount of acceleration that you get. Okay, so having said that, in today's experiment there will be an Atwood machine. Then it means like an Atwood machine means like you will have some kind of a pulley hanging like this, and then you will have like two masses. Like let's say you have mass 1, like on this side, and you can call this mass 1. Doesn't matter about the representation. And then you may call this mass 2. Then if mass 2 is greater than mass 1, then the whole system is going to accelerate in this direction. Okay, why it starts to accelerate? Because the reason is like this mass 2 is going to apply a force in this direction like this. That force is directly coming from as a weight, the weight of mass 2. And as you know, weight is defined as mass times gravity. For now, what we're going to do is like more or less for the lab's sake, we're going to keep everything as positive. In our lectures, what we dealt with is like gravity is always towards the center of the earth, and in our calculation we used gravity as negative all the time. But for now, let's just keep everything as positive as gravity positive, acceleration positive, even though it's moving downward. It's okay, let's not going to complicate that one. Just let's focus on the magnitude for now. Then weight 2 is going to pull the system like as indicated, and then mass 1 is not going to just simply start move, let the whole system fall. This system is not going to experience a free fall. The main reason is because weight 1, the weight of mass 1, is going to pull the system in this direction. Okay, so this is mass 2. Then this whole system is going to experience a net force of equivalent to, so the net force of the system is going to be, we're using just the magnitude for now, mass 2 times gravity minus mass 1 times gravity. Why are we minusing it? Even though both of them seem to act in the downward direction, but what is happening is like this system, like mass 2 is trying to pull the whole system in this direction, and then mass 1 is trying to pull this in this direction on the other side of the pulley. That means it's just like trying to one is trying to overcome the other one. Okay, so something that we need to keep in mind is like this is a college physics course, and it's not a university physics course. That we're not going to deal with any kind of inertia in the pulley. The pulley will be considered as massless. or okay, so it's a massless pulley. If it's massless, then the mass of the pulley is considered as nothing or zero. Okay, so this approximation is just only for the sake of like experiments, and it's not really like as part of the reality. But of course the experiment is going to give a perfect result. So the mass, if the mass of the pulley is considered as negligible, then there is something, a quantity, we call it inertia. Because of the rotational motion of the pulley, there will be something that will really incorporate or contribute towards the overall acceleration or overall this guy. But for now we are going to ignore that effect. We are just consider just the effect of the masses regardless of what the pulley's mass. Okay, so having said that, like the net force is equivalent to minus m2g minus m1g. That means the descending mass minus the ascending mass, right? So, but what we know is net force is mass times acceleration, right? So acceleration, we have acceleration first multiplied by mass. But when we consider mass, we need to consider the mass of the whole system. Okay, so therefore it's going to be mass 1 plus mass 2. Okay, then here g is a common factor, then probably I can take g out, right? So m2 minus m1 into g. Okay, then if I divide both sides of this equation by m1 plus m2, that is the total mass, then on this side m1 plus m2, what I'm going to get is like I can eliminate this by this. So therefore the acceleration of the system is going to be equal to mass 2 minus mass 1 divided by mass 1 plus mass 2. Okay, keep in mind when you are putting it in your calculator, don't forget the parentheses. Okay, multiplied by g. So in this way we are going to find the acceleration in our experiment. Okay, so this is like, you know, from theory, you can consider this is from theory. Okay, so you know, the theoretical kind of, even though we are going to, you know, put the masses and so on and so forth, but we're going to consider this as theoretical value. And then remember, g is equivalent to 9.8 meters per second squared. Okay, so remember to use that value. But on the other hand, I'm going to take you this. So this is one way of finding the acceleration of that pulley. But you may also find the acceleration of the system by something else, from kinematics. Okay, so from kinematics, okay, from kinematics, let's say that like you can measure the height dropped by mass 2. You remember, like you have the system like this, and then, you know, I represented this one by like that, right? So you have mass 2 like that, and then you have mass 1 like this, right? So when you let the whole system go, and then mass 2 is going to come down, and then he will hit the ground, right? So mass 2 will hit the ground. It's blue, let me use the blue. So mass 2 is going to come down and hit the floor. Okay, and then of course mass 1 is going to come over here. All right, so if you time the process, that means, like, you know, then you can measure the height, right? You can measure the height, this height, like how much distance m2 traveled from the beginning to the end. Okay, then if you can find the height or measure the height, just use a ruler or a tape measure, and then you can measure that. Okay, then if you know h, then you can use a stopwatch to time it. Like, for instance, you let this mass go, and then as soon as it hits the ground, what do? You stop the time. Then you're going to have time. Since this motion is starting from rest, then its initial velocity is 0. right? So from kinematics, what you know is, like the distance traveled in a uniformly accelerated motion, the initial time plus half times acceleration times t squared. But since the initial velocity is 0, then this term is going to disappear. You won't have that. So the result, what's going to be happening is, like, instead of d, what you have now is h, the height traveled by the descending mass, is equivalent to half times acceleration times t squared. If you do some kind of like crisscrossing and then elimination, if you multiply this by 2 and if you divide this side by t squared, then if you do the same thing on the other side of the equation, right, means what will happen is, like, this side will also be multiplied by 2 and then t squared. I'm going to show you better. Then what will happen is, like, these 2 cancels out, this t squared cancels out. Then your acceleration a is going to be 2h over t squared, right? So you're going to have another kind of acceleration calculation. So this is, this is a measured one. You can call this as measured. The lab manual says it measured acceleration. So you have a measured acceleration, and at the same time you have something from the theory. Then the overall exercise is going to be, now you will be measuring this. This is measured. Why we call it measured? Because you are going to measure the height. You are going to use a stopwatch to measure the time to find the acceleration. In the theoretical one, what you have is, like, you just have the masses and then you let the system go, and then using gravity you will just apply this equation. So now you have 2 equations. Okay, I'm going to write those 2 equations side by side so that, like, you can have them, like, so this is, let's put it like as t, acceleration theoretical, is going to be mass to the descending mass minus the ascending mass divided by the sum of the 2, and you multiply that by gravity. The other acceleration is the measured one. Acceleration measured is, what did we say? It is equivalent to 2 times h divided by t squared. Then now let's go ahead and then show you, like, how you are going to proceed with the whole system. So you go ahead and then, like, open your lab manual, and then your lab manual is going to show you, like, some theories and things like that. But the most important part is, like, read the procedures, because we are going to use the same procedure, except that the masses are going to be different. The masses are, I'm going to give you the masses, what masses you are going to be using for the whole thing. Okay, so in table 1, so this is your table 1 that looks like this. Okay, so now, since we are going to ignore inertial effect, and at the same time we are going to consider a frictionless system, okay, so we're going to ignore any of the stuff right under the asterisk. Okay, so ignore this, ignore this, and ignore this, and ignore this. Okay, then now I'm going to give you, like, a decent set of masses, what masses you are going to be using, and I'm going to show you, like, where you are going to get your distance values. Okay, so the masses that I want you to use for the first one is, like, use this directly. Okay, you don't need to change anything. Your descending mass in grams, you can keep everything in grams. Even when you do your calculations, you can keep your masses in grams, because the masses will cancel each other in the equation. Okay, so 64 descending, 54 ascending. This is one set. Okay, your set is going to be, what the next step is going to be, add a 50-gram mass on each of them. That will be 110, and this will be 100, and then add another 50 on each of them. This will be 160, and this will be 150, and then again add a 50, but our simulation system doesn't add a 50, so just add a 40 on this one. That means 200, because the maximum the simulation allows is 200 grams, so therefore just, but if you add 40 over there, add 40 over here. It's some kind of improvisation that we needed to do, so that, like, you know, the simulation will help us do the following. Okay. So the next step is going to be what? Is going to go to the simulation and then set the masses. I'm going to show you by filling this, the first one. The rest you're going to go out and then do it by yourself. Okay. So then what's going to happen is now we're going to just simply use one single run. We don't need to do 2 runs, 3 runs, or something like that. We're going to use just one simple, you know, for one height, and then you just simply do that. Okay. So what we're going to do is we're going to come to the simulator, and then we're going to, so this simulator, our descending mass is M1. It's fine. You can keep it that way, and our descending mass is this one. I mean, the ascending mass is this one and the descending mass is this one, because the system puts it that way. It's fine. But in our calculation, and the manual puts M2 at the descending and M1 as at the ascending. Okay. So click reset, and then, as we said, the very first mass that we need to as descending is 60. So we're going to have this to 60. So you can use the arrows to increase and decrease the amount of mass that you want to have. The manual or the simulation is not going to let you, you know, it always sets this at the descending mass and the one on the right at the ascending mass. So, you know, if this is 140, it doesn't let you go below that value. Okay, don't be alarmed. The only reason is like because always set your ascending mass first. Okay, so set this at 50 and then set this at 60. Okay, then what are we going to do? Let's go ahead and start the simulation. Okay, then start. Boom. Okay, then you may wonder, like, where the time and the height. Okay, you come to here to the table. You see the first column set of, it gives you a set of time and a set of position and a set of velocity data. We don't need the velocity data. What we need is, like, we're just gonna come here and pick time and position. Okay, again, this is a lab, so we're not going to, you know, take like 3 trials, because every time the system just tweaks the height a little bit here and there. So what we need is, like, just come to the very lowest part. Okay, see the 2 things that I shaded? Okay, so your time for your experiment is 0.742, and then the height, this is in meter, 0.2483. Then you come back to your data table and record the height. So this is in meter. So the height that we used is 0.2483. Remember, this value may vary, you know, because just the simulation doesn't keep it the same. So therefore, don't say like, oh, why my value is different from yours, because the simulator just changed this value. Okay, so as I said, one value is enough. That's it. That means you don't need to do 3 runs, just do 1 run. Then the time that I get for here is like 0.748. 2. Okay, so run 2, don't do run 2. You don't need to do it. Run 3, nothing. So therefore your average is going to be the same as what you got. So 0.742. Do you get my idea? What I'm trying to do? Then after that, then go ahead and then apply this formula. Okay, and then find the acceleration and then put it here. Okay, so we're not going to use, as I said, like M equivalent, because that M equivalent is something regarding friction and inertia. We're not using that, as I already said. So mass 1 plus mass 2, that means 60 plus 50, that is 110. Okay, that's in grams, so the parenthesis is in grams. Then the next is like frictional. Then this has to be ignored as well. There is no friction that we're going to deal with in our lab. Okay, we're keeping it simple. Okay, given the circumstances. Then M2 minus M1 doesn't matter. There it's M2 M1, but this is like 60 minus 50, which is 10. Okay, so that's your net force, 10 gram. Of course, this is in gram meter per second squared. Okay, so multiply that by 9.8. Okay, that would be approximately 98, right? So therefore your acceleration from theory is going to be what? 98. Don't say where I found, no, what, 98. 98 is 10 times 9.8 divided by this guy, the total, right? 110. Or you can just directly apply the equation, the first equation that I showed you. Okay, then using this you get another acceleration. So you have two accelerations. Like now you have this acceleration from theory, you have this acceleration. Not this one, this one. I already tick marked it. Then compare those two and then find the percent difference between the two. Then follow the same procedure. Okay, then reset the masses to 110 on 100 and then get the distance that it gives you. Again, the distance is the very last value on the second column, and the time is the very first on the first column, the last value. Okay, and that's how you fill out like the first data table. Then you proceed to the second data table. The second data table, it asks you, like, you're going to apply the same two equations, but in this case the idea is to keep the total amount of mass in the system as constant. Okay, so it's going to be the same procedure. I'm not going to go ahead and then, like, repeat it. There is no any kind of friction, so there is no equivalent. Then there is no any kind of inertial calculation. It's crossed out. And now mass 2, that's the descending in grams, the ascending in grams, it's fine. Whereas the height is going to be in meter. Then now, what are the masses? I'm going to give you those set of masses. Please use those set of masses for your experiment. For the descending, 150. For the ascending, 145. Okay, I'm not using strictly the values given in the manual because the simulator doesn't accept those ones, and I found this simulator very well aligned with what we do in the lab practically. So as a result, just this is going to be really more than enough, like, to do the labs, like, virtually. Then the very first is 155 plus 145. If you add those two, the total is 300, right? So what we are going to do is we're going to add a 5 gram on this one, right? If we add a 5 gram on the descending one, this will be 160. And then we're going to take away 5 grams from here. This will be 140. Look, the total here is 300. The total here is 300. Again, on the next step, what we will do is, like, add 5 on this one, it will be 165. Take 5 away from this one, that will be 135. Still the total will be 300, right? Then again add 5 on this one, 170, and then okay. So just use those masses, you know, don't have to change them, just use those values. Okay, again, like, I don't want you to do 2-3 trials. I mean, why do we need to do 3 trials in a practical case? Because we're going to make errors, like, you know, this is mostly, it's a computer simulated data or information that you get from a computer simulation. The most likely the error margin is really low. So now you go ahead and then, like, I'm going to show you one set of this. Then we're going to use 155 on the descending one and 145 on the ascending one, and then we're going to do the simulation. Okay, you come here, click reset, and then what do? Go to 155 on the descending, and on this one go to 145. Total is 300. Okay, then what do? Click start, you let the model run, and then you come to the data table. What do? Pick the last value as your time. Okay, your time is now 1.2 approximately. Okay, 1.2, and your descending height is now 0.2244. okay, then what do? You're going to come here and plug in the height. The height is 0.244, and the time is, of course, it's 1.2 seconds. Then the average is going to be the same, because the average of a single value is itself. Then you apply this, and of course you're going to get your values in meters per second squared. Okay, then get your measured acceleration. The total mass here, so you don't have M equivalent. M equivalent is 0, or ignore it. Then the total is here 300 grams, right? That's what we said. Okay, and then mass 2 minus mass 1, we don't have friction, we're not considering any friction. Okay, so this one has to be crossed out as well. Okay, then now what will you do? Mass 2 minus mass 1, that means 150 minus 145, that's a 10 gram difference. So 10 gram multiplied by 9.8. This is not in Newton, this is like in gram per gram meter per second square. Okay, you know, the unit for now is, this unit is going to be in parentheses. Yeah, over here you have to put meter per second squared, but of course gram, it's not kilogram. Kilogram meter per second squared has a special name known as Newton, right? So what will happen? This will be 10 times 9.8, which is 98. Divide that by what? By 300. Okay. 10 times 9.8 is 98. So the 300 came from here. Okay. Then using that calculation, you put your value here. Then you compare this value and this value using the percent difference between the two. Remember, percent difference is calculated as one data minus the other data or value divided by the average between the two. That's how you do the simulation. Very simple, but very effective. I want everyone to do the way I just mentioned. Then good luck. Thanks. See you later.